All right, here's a really quick example where you could use a starting equation to derive something that apparently seems unrelated. So I'm just going to start with an equation for the displacement of a particle. So I'm not going to go into what the particle is. Let's say it's something in a particle accelerator. Doesn't really matter. Okay, so this is the equation that gives us the displacement over time. The question I'm going to ask us to complete is, I want an equation for force as a function of time. So what we need to do is, again, work the problem from both ends as we normally would. We've got to think what we could do to get an equation for force. We know that F equals ma, F equals change in momentum over time, and therefore would be dp by dt. We know that P is mv. There's lots of ideas we could have. Working it from the other side as well, we've got an equation for S in terms of t. So I know if I take the differential of that, that's going to give me velocity. And if I take the second differential of that, that's going to give me acceleration. Hopefully suddenly I've just seen the link. I now know what I'm going to do. So what I want is to get an equation for the acceleration based on this equation. Right, let's do that first. So if we take the first and then the second differential of this with respect to time, so if we start with ds by dt, that gives us, reduce the power by 1, multiply by the power first, 12t squared minus 0.1, the 10 disappears. That this gives us velocity. Take the second differential. Again, drop the power down by 1, multiply by it first, gives us 24t, and the 0.1 disappears this time. And that, by definition, gives us acceleration. So essentially what I've got is an equation for acceleration as a function of time. If we assume that this object has a constant mass, then making a second equation for mass is as simple as using the equation for acceleration as a function of time. So quite simply, our force as a function of time equation is 24 mt. Couldn't be easier.